Welcome back, everybody. It's awesome to have you here with us today as we continue our journey through the transformative insights from Dr. Alok Aggarwal's captivating book, The Fourth Industrial Revolution and 100 Years of AI.
It feels like just the other day we were wading through all those sticky ethical questions about data, scrubbing out bias and the whole mess of ownership and consent. And then there's the potential of that synthetic data.
Oh yeah, that was a fascinating one.
So we've talked about all that. But what happens when that data, is used to create these super powerful AI systems? The kind that are so complex, even the experts have a hard time explaining, like how they make decisions.
Yeah, it's like AI is giving us answers, but we don't even know how it got there.
Exactly.
It's a bit unsettling, isn't it?
It is. And that's where we're headed today. We're diving into this really cool world of explainable AI.
XAI for short.
Yeah. It's basically like telling our AI, hey, show your work. Don't just give us the answer. We want to understand the thought process behind it.
Exactly. Like we're not just going to take your word for it. We need to see the reasoning, the logic.
Dr. Aggarwal makes this really compelling argument. He says we got to shift AI from being this mysterious black box to something more like a
transparent glass box.
Yeah, a transparent glass box. Love that analogy.
Today we're exploring the critical importance of AI transparency, diving into techniques for interpreting complex AI models and asking a profound question. Can we truly understand causality in these advanced systems?
We'll unpack why transparency matters, examine methods to peek inside the black box of AI, and challenge ourselves to understand how these incredible technologies actually make decisions. Okay, so first things first. Why should we even care about making AI explainable? I mean, it seems like AI is doing just fine on its own, right? Pumping out these predictions, making decisions. What's the big deal?
Well, think about it this way. Imagine a medical AI system, right? And it diagnoses you with some kind of rare disease.
Uh-oh.
Wouldn't you want to know how it came to that conclusion?
Absolutely. Yeah, I definitely wouldn't just blindly trust that.
Exactly. It goes way beyond just trusting the AI. It's about making sure that this AI, this powerful tool, is something that we can use responsibly and effectively.
Okay, that makes a lot of sense. It's not just about blind faith, it's about having a deeper understanding.
Right? And, the book doesn't just stop there. It actually lays out 4 key benefits of XAI.
4 key benefits. Okay, I'm intrigued. What are they?
It calls them justification, knowledge discovery, algorithm improvement, and enhanced control for those subject matter experts.
Wow. Okay, so there's a lot more to unpack there. Justification. That one seems pretty straightforward, like you were saying with a medical example. The AI needs to be able to back up its diagnosis.
Right, it's like asking why. Show me the evidence, the chain of reasoning. We need that, especially when decisions have high stakes.
Makes sense. Okay, what about knowledge discovery? That one sounds super intriguing. Is the book suggesting that AI could actually teach us something new?
Yeah, sometimes. And this is kind of wild. AI will make these predictions that are spot on.
Okay.
But they just seem counterintuitive to human experts.
Like we don't understand how it got there.
Exactly. And that's the exciting part. If we can delve into the AI's reasoning, we might uncover these hidden insights.
Oh, wow.
New patterns in the data. Things we never even considered.
So, it could be like a tool for scientific discovery then.
It really could. It's mind-blowing.
Yeah, that's pretty incredible. All right, algorithm improving. I feel like that was pretty self-explanatory, right? We're talking about making our AI systems even better.
Exactly. If we understand why an AI makes certain decisions, we can pinpoint its weaknesses, any biases it might have. And once we know that, we can improve the system, make it more accurate, more reliable.
So we're always striving for better AI. Okay. And the last one, enhanced control. So who's really in control here? Us or the AI?
That's the million-dollar question.
Yeah.
And that's exactly where explainable AI comes in. It gives the control back to the humans, the experts in their fields.
So the doctors, the engineers, whoever is using the system.
Exactly. When they understand the AI's logic, they can spot errors, vulnerabilities, and know when and how to intervene.
So it's not about AI replacing human expertise. It's more like
it's about empowering humans.
Empowering humans. Yeah, to use AI as this incredibly powerful tool. But what about the flip side? What are the dangers of these black box AI systems when we don't have that transparency?
Well, if we don't know how they're making decisions, It's almost impossible to anticipate problems or prevent errors. They can be really brittle, working great in some situations and totally falling apart in others. And if something does go wrong, it's really hard to figure out what happened or who's responsible.
Yeah, that lack of transparency could even lead to people just not trusting AI.
Oh, absolutely. They might be hesitant to use it, even if it could be beneficial.
So the big question is, how do we move away from these opaque black boxes and create these transparent, explainable AI systems?
Right? How do we crack them open?
Yeah, so the book actually gets into some specific techniques for explaining those AI models.
It starts by acknowledging this really fundamental trade-off between accuracy versus explainability. Simpler models like linear regression, those are usually easier to understand, but they might not be as accurate as the more complex ones.
Like those deep learning networks everyone's talking about. So it's a balancing act, finding the right level of complexity for whatever you're trying to do.
Exactly. The book focuses on 4 linear models that do a pretty good job of balancing this. They're linear regression, logistic regression, generalized linear models, GLM, and then generalized additive models, or GAMS. These models all work on this core concept, weighted sums.
Weighted sums. Okay, so these models use weighted sums to make predictions. Can you break that down a bit? What does it actually mean, and how does it make them more explainable?
Sure, think of it like a recipe. You've got all these ingredients, those are your features.
Right?
And each ingredient has a certain weight that determines how much it contributes to the final dish. Your prediction in these linear models, it's pretty straightforward. The output is just the sum of all those weighted ingredients.
Okay, I'm starting to see how that makes the AI's reasoning easier to follow. We can see how much each ingredient or each feature matters.
Exactly. Let's take linear regression, and we'll use it to predict housing prices.
Okay, good example.
So the size of the house, that might have a big weight, right?
Bigger house, higher price, usually.
Exactly. It's a major factor. Then you've got the number of bathrooms, maybe that has a smaller weight, and then something like the color of the front door, that might have a tiny weight, almost negligible.
So we can see what factors the AI is considering, but also like how important each factor is. That's pretty cool.
Right? And that level of transparency, that's what makes these linear models so valuable, especially when explainability is key.
Okay, that makes sense. So that was linear regression. What about logistic regression? How does that fit into the whole weighted sum idea?
Logistic regression, it's similar, but instead of predicting like a specific number, like a house price, it gives you a probability.
So, like a percentage chance of something happening.
Exactly. Let's say a bank is using logistic regression to try and detect fraudulent transactions.
Okay.
They look at things like the transaction amount, the time of day, the user's location, assign weights to each of those factors, and then the output is a probability score. Basically, what's the percentage chance this transaction is fraudulent?
Okay, that makes sense. Still using weighted sums, but the output is a probability instead of a hard number.
What about GLMs and GAMs? Are those also based on this weighted sums idea?
Yeah, they're built on that foundation. GLMs let us supply weighted sums to situations where the relationship between the input and the output might not be perfectly linear. Like imagine we're predicting how many customers visit a store each day.
Okay.
That number probably follows a certain kind of pattern, a probability distribution. A GLM lets us model that pattern while still keeping things transparent with those weighted sums.
Interesting. So it's adding a layer of complexity, but we're not losing that transparency.
Right, and then GAMs, they take it a step further. They allow for even more flexibility. They can handle some nonlinear relationships between those features in the output, but they still keep a degree of explainability because each term in the model is just a function of one feature.
So GAMs are getting a bit closer to those more complex models, but we can still see how each piece contributes to the prediction. It's all about striking that balance.
Right, but you mentioned earlier that these linear models have limitations, so they assume that features are independent of each other.
Yeah, and that's a key point. In the real world, things are usually interconnected. Think about that housing example again. The size of the house, it's probably related to how many bedrooms and bathrooms it has. Linear models, they have a hard time accounting for those kinds of relationships.
So they're great for explaining simple relationships, but might miss the bigger picture in more realistic situations.
Exactly. And that's where researchers are always trying to find ways to make even the really complex AI models more transparent. But before we get into that, let's shift gears a bit. Let's talk about another really powerful tool for explainability: decision trees.
Okay, I've heard of those. Are those kind of like those choose-your-own-adventure books where you make a choice and it takes you down a different path?
Yeah, imagine a tree, right? With branches, and each branch is like a decision point, and those decisions are based on a specific feature. So the tree, it splits the data into smaller and smaller groups, and that leads to a final prediction.
So it's like following a set of rules step by step to reach a conclusion.
Exactly. Dr. Aggarwal has this great example in his book. It shows how to predict customer purchases based on things like income, gender, and age.
Okay, walk me through it.
All right, so let's say the first branch, it splits based on income. Is it above or below, say $50,000 a year?
Okay,
Then the next branch, maybe it splits based on gender, and so on. Each decision point sends you down a different path in the tree until you get to the end where you have a prediction: buy or don't buy.
I can see how that would be easy to understand, even for someone who doesn't know much about AI. You can literally see how the decision is being made.
Exactly. That's the beauty of decision trees. Everything is transparent, easy to follow.
But are there any downsides to this approach?
Well, they can get pretty complicated if you have a ton of features and decision points, and they can be sensitive to little changes in the data. A slightly different dataset could give you a totally different tree structure.
So, they might not be the most adaptable or robust solution for every situation.
Right? But they're still super valuable for explainability, especially when that transparency is crucial. Now, I bet you're thinking, what about those really powerful AI models, the ones even the experts struggle to understand?
You read my mind. Those deep learning networks, they seem almost magical but kind of scary because we don't really know how they work.
Well, that's where things get really interesting. It's like the cutting edge of XAI research, figuring out how to make these things explainable. The book talks about how these models, they mix up inputs in ways we don't fully get. And the math they use, oh man, it's like nonlinear algebra.
Yeah, that's a bit beyond me.
Heavy-duty stuff. It's not easy to figure out how they reach their conclusions.
So, is explainability just a pipe dream for these complex models, or are we just stuck with the black box?
Not necessarily. There are some really cool techniques being developed. One that's showing a lot of promise is the use of surrogate models.
Surrogate models. Okay, I may need a little help with that one. What are they and how do they make things more explainable?
Imagine you're trying to recreate like a famous chef's signature dish, but you don't know the recipe.
Okay, I see.
You might try different ingredients, techniques to get a dish that tastes similar even if you don't know the original chef's exact process.
So surrogate models, they're kind of like simplified versions of those super complex AI models. They try to predict the same things, but in a way we can actually understand.
It's like creating a map of, say, a really complicated mountain range, but using simpler symbols and landmarks to make it easier to navigate. You might not get every little detail, but you'll get a pretty good idea of the overall landscape.
I like that. That's a great analogy. But it sounds like there's a trade-off here. Like surrogate models, they might not be as accurate in order to, gain that interpretability.
That's true. That's a valid concern. And it really shows the constant tension between making AI models accurate and making sure we can actually understand how they work. It's a balancing act, a real challenge for researchers.
So it's not always about getting the most accurate prediction. Sometimes we need to make sure we can understand how the AI is working, especially in areas where transparency is so important.
You got it. It's about picking the right tool for the job. And speaking of tools, researchers have developed some pretty fascinating techniques to help us understand AI decision-making. These are called model-agnostic techniques, and they're like universal translators for AI.
Wait, universal translator for AI. Okay, now I'm really curious. Tell me more about these model-agnostic techniques. How do they work? Why are they so important?
Well, imagine if you had a tool that could help you interpret the decisions of any AI model, no matter how complex or how it was designed.
That would be amazing.
That's exactly what model-agnostic techniques do. They give us a consistent framework for analyzing and comparing different AI models. Super valuable in a field that's as diverse and fast-changing as AI.
So it's like having a common language for understanding AI, regardless of how each specific model talks, right?
Exactly. It's about creating this shared understanding, being able to compare different approaches. Super helpful when you got to choose the best AI model for a task, or when you need to explain AI's decisions to people who aren't, AI experts.
That makes sense. It's all about transparency and accountability. Even though we're dealing with complex AI, are there different kinds of model-agnostic techniques, or do they all work in the same way?
They come in different forms, each with its own pros and cons. A big way to categorize them is to divide them into local and global techniques.
Okay, what's the difference?
Local techniques zoom in on specific predictions, like why did the model make this particular decision for this specific input?
So like, why did Netflix recommend this movie? Or why did the bank flag this transaction as maybe fraudulent?
Yeah, exactly. It's about understanding the reasoning behind specific decisions. Global techniques are different. They take a broader view, trying to give us a sense of the model's overall behavior. They help us understand the general patterns between inputs and outputs rather than individual predictions.
So, local techniques are like looking at individual trees, while global techniques are like studying the whole forest.
Perfect analogy. And within these categories, there are a bunch of well-known model-agnostic techniques that are super popular among researchers and people using AI in the real world. 5 big ones are partial dependence plot, permutation feature importance, individual conditional expectation, local interpretable model-agnostic explanations, LIME, and shapely values, SHAP.
Okay, well, that's a lot, and it sounds like we're getting into pretty technical territory. Should we maybe dive a bit deeper into some of these techniques?
Maybe a quick overview of a couple of key techniques would be good. Let's focus on partial dependence plot, permutation feature importance, and individual conditional expectation. These are all global techniques that can give us a good understanding of how AI models behave overall.
Sounds good to me. Let's start with partial dependence plot, or PDP. What exactly can we learn from this technique?
Okay, imagine you have a model that predicts housing prices. It uses different factors like location, size, number of bedrooms, and all that.
Okay.
A PDP would shows you how the average predicted house price changes when you adjust one specific feature, let's say number of bedrooms. But all the other features, they stay the same.
So it's a way to see how one feature impacts the predictions, everything else being equal. Got it.
Exactly. It lets you visualize that relationship between the feature and what the model predicts. For example, you might find that, as the number of bedrooms goes up, the predicted house price also goes up, but only to a certain point. Then adding more bedrooms might not help as much or could even make the predicted price go down.
Interesting. So it's like finding the sweet spot for that feature, right, where it has the biggest positive effect. What about permutation feature importance? How does that one help us understand AI?
Permutation feature importance. It's a smart way to figure out which features are the most important for the model's decision-making. It's like playing a game of what if with the model's inputs.
A game of what if. Okay, tell me more.
Imagine we have a model. It predicts customer churn for a phone company. We have all this data on customer stuff like how much their bill is, how much data they use, how long their contract is.
Makes sense.
To figure out how important each feature is, we randomly shuffle the values for just one feature at a time, and then see how much that messes up the model's accuracy.
So it's like, shuffling a deck of cards where each card is a different feature. Then we see how much the game changes when we shuffle just one specific card.
Exactly. If shuffling a certain feature's card makes the model way less accurate, then that feature is probably really important. But if shuffling another feature's card doesn't change much, then that feature is probably not that critical.
So it's a way to measure how much each feature matters by messing with its values and seeing how much that hurts the model.
It's really clever.
Okay, we've got partial dependence, plot, and permutation feature importance. What about individual conditional expectation, or ICE? How is that different?
So PDP shows us the average effect of a feature across all the data. ICE is more personal. Instead of just averages, ICE plots a separate line for each individual data point. It shows how the prediction changes for that one specific instance as you adjust the feature.
So it's like making a custom prediction path for each data point, showing how the prediction would change if we tweak that one feature.
Exactly. It's super helpful for understanding why the model might make different predictions for data points that seem similar. It can help you spot those weird outliers or little groups within your data that aren't following the average trend.
Like a magnifying glass.
Yeah,
We can zoom in and see the tiny differences that might be hidden in the bigger picture.
exactly. It's all about uncovering those layers of complexity and really getting a handle on how these models tick. And these are just three of many, many powerful tools we can use to interpret AI. They all provide a unique way to look at these complex systems.
This has been an awesome journey so far. It's clear that understanding how AI models work is becoming more and more important, especially now that they're playing such a big role in our lives.
Exactly. And you know what's really interesting to me, this whole causality aspect, it actually builds on what we've been talking about so far in this deep dive.
Oh, you mean explainable AI and all that?
Yeah, like we keep saying, we want AI to explain its decisions, right? Tell us what it's thinking.
Right, so we can trust it more. See if it's making sense.
Exactly. And we talked about how interpretable AI helps us peek under the hood, see how the models actually make those decisions.
Right? Like what factors it's weighing, all that.
But causality, this adds a whole other level on top of that.
Okay. Yeah, I can see that. So first things first. I think we need to define this. What exactly is causality? I mean, it's more than just two things happening at the same time, right?
Exactly. It's not just correlation. Causality means one thing actually makes another happen, like a direct cause and effect relationship. And even more than that, it's about understanding how much each cause contributes to the effect, if that makes sense.
It does. It's like knowing that pressing the gas pedal makes the car go. It's not just that they happen together. One actually makes the other happen.
Yeah, that's a good one. And the strength of that connection, like how hard you press the pedal, influences how fast the car goes. That's also part of understanding causality.
Right? So we humans, we seem to just get this causality thing. But even we mess it up sometimes, right? Dr. Aggarwal talks about that example from way back in the 1950s, when scientists were trying to prove smoking causes lung cancer.
Oh yeah, that was a big debate for a while.
People were saying, well, maybe it's something else, some other factor, right? It wasn't immediately obvious.
Yeah, and that really highlights how tricky it can be to prove true causality, even for us with our big brains.
Right? Like it took a ton of research and evidence to show that link between smoking and lung cancer definitively.
Exactly. It's not always a simple A to B connection. And that's what makes this whole AI thing so fascinating.
Because if we struggle with it sometimes...
How do we teach a machine to do it?
Exactly. So that brings up like the million-dollar question, right? Can AI ever really grasp this whole cause and effect thing? I mean, if it doesn't think like us humans, how can it understand these complex relationships?
That's a great question. And that's where the work of folks like Judea Pearl comes in. Back in the 1990s, he and others really started tackling this head-on. And their breakthrough was something called causal Bayesian networks.
Causal Bayesian networks. Okay, that sounds pretty complex, but the basic idea is pretty cool. Imagine like a giant web, right? And each dot on the web represents a concept or a variable.
Okay, I'm picturing it. So the lines connecting those dots, those represent the causal relationships between them. So the thicker the line, the stronger the cause and effect relationship.
Yeah, so it's not just looking for patterns like traditional AI, it's actually trying to map out how things cause each other.
Exactly. And these networks can analyze tons and tons of data to figure out those causal relationships, even when they're super subtle.
Wow, so it's like teaching AI to think more like a scientist, like testing hypotheses and figuring out what really causes what.
Exactly, and that's why this whole field of causal AI is so exciting, because it has the potential to completely change the game.
Yeah, okay, I'm starting to see that, but let's bring it back down to earth for a sec. Why should the average person listening care about all this? Like, what's the real-world impact of causal AI?
Think about it. Imagine if we had AI that could tell us why climate change is happening. Not just show us scary graphs and data, but actually pinpoint the main drivers. Or doctors using AI that can diagnose based on the root cause of your illness, not just your symptoms.
Oh, wow. Okay, that's big.
Right? It's not just about treating the symptoms. It's about tackling the source of the problem. And that could revolutionize healthcare.
Absolutely. And it's not just healthcare, right? I mean, you could apply this to almost anything.
Exactly. We're talking law, product safety, and even military strategy. Any field where understanding the why behind the what is crucial, causal AI could make a huge impact.
Wow. So to recap for everyone listening today, we've talked about a lot of really complex but super important stuff. First, we visited Explainable AI, where we want AI to tell us its reasoning, right? Be transparent.
Lift the curtain a bit.
Then we talked about Interpretable AI, which is all about understanding how the AI model actually makes those decisions, like looking at the code and the algorithms.
Peeking under the hood, so to speak.
Exactly. And finally, we dove headfirst into this whole new world of causal AI, which, like we said, is all about teaching AI to understand cause and effect relationships. And that, like you were saying, could be a total game changer.
Absolutely. It has the potential to revolutionize so many fields.
But there's always a but, isn't there?
Of course, building truly valuable AI systems is about more than just making them explainable, interpretable, and causal. We also need to make sure they're being used fairly and ethically.
Ah, yes, the ethics of AI. That's a whole other can of worms.
It is a very important can of worms, and that's actually what we're going to be discussing in our next deep dive. We'll be exploring fairness in AI and ethical AI.
So make sure to tune in for that. We'll be tackling some big questions like, are all these characteristics, such as explainable, interpretable, causal, fair, and ethical, always necessary for AI systems to be valuable? Are some more important than others? It's going to be a fascinating discussion, so don't miss it.
And in the meantime, think about this. We've talked a lot about how we can make AI better, but what happens when AI starts understanding cause and effect better than us? What does that mean for the future? Just something to ponder.
Ooh, that's a good one. All right, everyone, thanks for joining us for this deep dive. Catch you next time.